haven't joined yet. Okay, so this is the first section, which is multiple choice questions, and I would prefer we do that orally together. Okay. It says question number 1: a student wishes to use a magnetizing coil to make a permanent magnet from a piece of metal. Which metal should she use? Okay, Malak?
Steel?
Steel is the answer. Yes, correct. So the answer is steel because steel is a hard magnetic material. Iron is soft magnetic, we don't use it. Copper and aluminum are non-magnetic at all. Good, 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 Malak. Question 2. The diagram shows... Hold on, someone's here. Dana. Okay. Question 2 says the diagram shows a transformer. They gave us the input, they gave us the number of turns, and they want the output voltage. So what is the output voltage? What is the output voltage? If you know the answer, you can raise your hand. If you need time to calculate, then calculate. What is the output voltage? Anyone? Question 2. Very simple question. Yes, of course I can solve it. But let's just wait for the rest of you. Does anyone have an answer for question number 2? Okay, to answer this, I think Nujud 50 volts. Okay, let's see. I'll say, let me just bring that down a little here. I'll say V1 over V2 equals to N1 over N2. It's V1. Very simple formula. V1 input voltage 100 over V2 equals to 40 over 80. Okay, I can cancel out these and I can say by 1 by 2, then cross multiply V2 equals to 200. 200, it's the step up transformer. Because when the number of turns increase from the primary to the secondary, the voltage increases by the same ratio. So the answer for this question is C. The answer is 200 volts. Okay, does that make sense, all of you? 200 volts. Okay, please communicate, all of you. Thuraya and Sama, Dana. Okay. Question 3. It says a metal rod XY is placed near a magnet and X is attracted when it is placed near the north pole of the magnet and also when it is placed near the south pole of the magnet. How does end Y behave when it is placed in turn near the two poles of the magnet? So what happens to end Y? Question 3. Who has an answer? Okay. Malak? Yes, Malak.
Can it be C?
Repulsion and attraction. Okay, Malak says
Yes.
C. What about you, Sama? Sama, is your microphone working? Guys, try to talk to me. Let's make it more interesting. Talk to me, guys. Thuraya, what do you think?
C as well.
Repulsion and attraction. Okay. Dana, C as well?
Yes.
Okay. Now, if and X is attracted to the North Pole and an X is attracted to the South Pole as well, what does that tell you about the material of this rod? Is it a magnet? Can I say that this is a magnet? It's not a magnet. It's not a magnet, because if it was a magnet, X would be, for example, attracted here and repelled here. It's not a magnet. So if it's not a magnet, it means that it's a magnetic material. So magnetic materials can be attracted, just attracted, never repelled. So if I use end Y instead of end X, this means that Y would be attracted as well to the North Pole, and Y would be attracted as well to the South Pole. So the answer for this question is A. Okay? The answer for this question is A. There wouldn't be any repulsion, because this is a test for magnetism. If X is attracted to the North Pole and X is attracted as well to the South Pole, this means that this material is just a magnetic material. It can be attracted to any magnet. So even if I used end Y, it would also be attracted to the North Pole and it would also be attracted to the South Pole. So there wouldn't be any repulsion here. So the correct answer is A. Does that make sense? The correct answer is A. The correct answer for this question is A. Is that clear, all of you? Okay. Okay. So, Dana, is it clear?
Yes.
All right. Moving on. Question 4. Okay. How can a permanent magnet be demagnetized? You have A, cool the magnet, hit the magnet repeatedly, leave the magnet in a coil which carries direct current, pass a small current through the magnet. Which one is the correct answer? How can I demagnetize a permanent magnet? Okay. I'll pick Thuraya. I'll pick the quiet ones from now on. Thuraya, how can I demagnetize a permanent magnet?
B, you hit the magnet repeatedly with a hammer.
Yes, that's correct, Thuraya. Correct. You hit the magnet repeatedly with a hammer. Good job. An electromagnet is used to separate magnetic metals from non-magnetic metals. Why is steel unsuitable as the core of the electromagnet? because it's a good conductor of electricity, it forms a permanent magnet, it has a high density, or it has a high thermal capacity. Which one of the four answers is correct? And I'll pick, okay, Malak?
B.
B. It forms a permanent magnet. Because steel forms a permanent magnet, steel is not suitable. That's why we use, what do we use instead of steel?
Iron.
Iron. Yes, we use iron. Good. So, after that, we have the diagram shows a solenoid connected to a sensitive voltmeter. Which of the following would give a zero reading on the voltmeter? Holding the magnet stationary, moving the magnet away from the solenoid, moving the magnet towards the solenoid, moving the solenoid towards the magnet. Which one of the four options here would give a zero reading on the voltmeter? And I'll direct the question to Hassan. Hassan, can you hear me? Okay, Najud is back. Hassan, are you here? All right, I'll go to Sama. Sama, which one of the four answers is the correct answer for question number 6? A. Sama, isn't your microphone working? Okay, so the answer is A. Why is it A, Sama? Oh, okay, now I understand. Sorry, it's okay, Sama. My fault. I understand. Thank you. So the answer is A. The answer is A. The answer is A because when the magnet is stationary, there is no changing magnetic field. There is no cutting of magnetic field lines. That's why the voltmeter gives a zero reading. But when I move the magnet away from the solenoid, there is a changing magnetic field. When I move the magnet towards the solenoid, there is also a changing magnetic field. Even when I move the solenoid towards the magnet, the same thing happens. But if the magnet is stationary, there is no changing magnetic field, so the voltmeter would give a zero reading. Good one, Sama, thank you. Another question about a transformer. That's also a very simple. The equation in 1 over n2.
Mister?
Yes.
Can we repeat why the question 6 is A?
Yes, Najud, of course. Question 6 was A again because if the magnet is not moving, there is no changing magnetic field, or there is no cutting of magnetic field lines. For a current or an EMF to be induced and detected by the voltmeter, the magnet needs to be moving, or the solenoid needs to be moving, so that magnetic field lines are cut and an EMF is induced. This is if you remember when we talked about electromagnetic induction as the first thing we talked about in this chapter. So the magnet needs to be moving in order for magnetic field lines to be cut, inducing an EMF. So if the magnet is stationary, there is no cutting of magnetic field lines, so the voltmeter would read 0. Make sense? Now, question number 7. Again, N1 over N2 equals to V1 over V2. So, same thing, 25 over V2 equals to 50 over 100, 50 over 100. So I can just simplify. 25 over V2 is a 1 over 2. V2 is 50 volts. Okay? You cross multiply, V2 is a 50 volts. So the answer is B. Okay. Question number 8. A straight wire carrying a current produces a magnetic field. Which diagram shows the correct shape of the field? Dana, which one of the 4 diagrams show the correct shape of the field? Dana? Seven? Malak, 7 is here. This is question 7.
I'm not sure, but is it D?
Hold on, okay, it's D. Yes, Dana, your answer is correct. It's D. It circles around the wire. Okay, and the circles gets further and further apart as we get further away from the wire. So the answer is D. Okay. Malak, question 7. What's the problem with question 7?
Oh no, at first I didn't simplify it completely. I used 5 over 10, and then when I cross-multiplied, I got 12.5. But I didn't simplify it completely, I guess that's why. But then when I solved it again, I got a 50.
Okay, good. Question number 9. A student carries out an experiment, and this question is for Nujud. Nujud, pay attention. A student carries out an experiment to see the effect of a magnetic field on a wire carrying a current. The wire moves upwards as shown. What would the student do to make the wire move downwards? A, B, C, or D?
I think D.
Use a stronger magnet. Are you sure? It's not D. Who has an answer? Sama, type your answer if you have an answer. A, B, C, or D? Yes, A. A. Reversing the direction of the current would reverse the direction of the force. Okay? And this is using Fleming's left hand rule. Okay? It's all about reversing things. If they said reverse the poles of the magnet, it would also reverse the direction of the force. But using a stronger magnet would simply create a stronger force. So the answer is A, Nujud. A brass rod is positioned in an east-west direction, and a plotting compass is placed at each end. Which diagram shows the positions of the needles of the plotting compasses? A, B, C, D. Each one of you, I want you to type in your answer in the chat column. Let's see if we're going to have same or different answers. Question 10, please. Read the question carefully and type in your answers. Okay. Najud said B. Come on, each one of you, I want to see your answers. A, B, C, or D. Thuraya said A. Okay, we have Malak. Dana said B. Malak said C. Sama? A. Okay. Thuraya, why did you say A? Thuraya, can you hear me? Why A? I don't know if Thuraya can hear me, but the correct answer for this question is A. A is the correct answer. Why? Because both compasses are gonna point in the direction of the north. Nothing is gonna, the brass rod wouldn't affect the compasses because it's a brass rod. It's not a magnet. It's not a magnet. It doesn't have any magnetic effect. Okay? So the compasses wouldn't be affected by the brass rod. The compasses would point in their natural direction, which is towards the north. So this is why the answer is A. Alright? The answer is A. Got it? So Sama, correct. Thuraya, correct. The answer is A, and I hope that you understood why the correct answer is A. Cool? Okay. So this concludes the first section of the paper. Omar, you're late. And I can't hear you. Just leave the meeting and try to join again. I can't hear what you're saying now. Alright. Let's go to the next section, which is the short questions. Alright?
Mr. As I said, I'm sorry, we actually had a power cut and the power just came back, so I really apologize for coming late.
Okay. Going to the next section, which is the short answer questions. Use the information above to calculate the number of turns on the secondary coil. Start. Please try to have a pen and a paper in front of you. Do the calculations. and type in your answer in the chat column. Let's do that. Okay. Okay, I don't see any answers so far. No answers. Okay, 12. Malak said 12. What about the rest of you? People try to calculate faster. It's a very simple formula that you need to use. $12. Okay. All right. So Umar got 12. Malak got 12. And the rest of you are sleeping. The rest of you are sleeping. Okay, so Thuraya, Dana, Sama, Nujud, where are your answers? Are you facing difficulties calculating it, Sama and Nujud? Okay. 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 You have 240 volts in the primary. You have 6 volts in the secondary coil. You have 480 turns in the primary coil, and you want to find the number of turns in the secondary coil. This is my solution. V1 over V2 equals to N1 over N2. Then we cross multiply. Then we make N2 the subject, so it ends up to be 12 turns. Does that make sense?
Sir, I did something different.
What did you do?
I did 240 over 6 equals to 480 over n. Then I made it 40 over 1, which equals to 480 over n2. Then I multiplied it. It became 40 n2 equals to 480. So then I divided I divided 480 by 40, then I got 12.
That's correct. That's correct. That's the right way to do it. That's the right way to do it. Alright? Good, Malik. So the V stands for voltage and the N stands for the number of turns each coil has. Yes. V1 is the voltage of the primary voltage. V2 is the secondary voltage. N1 is the number of turns in the primary coil. And N2 is the number of turns in the secondary coil. So, yes, Thuraya. Good? You get it now? Alright, we'll go slowly, step by step, step by step. This is the aim of revising the whole chapter. Describe how a transformer works. Okay? Describe how a transformer works. It's a 3 marks question. Raya, can you mute the microphone, please?
Eternity.
Thuraya, can you mute your microphone? Thank you. Thank you.
Mister, can I answer?
Yes, Roman. It's a 3 marks question. So how does a transformer work? How can I get the 3 marks out of this question?
Okay, a transformer is an apparatus that like makes the current either go up or down using magnetic induction, and not any current, only alternating current. That it can change the voltage. It can increase it or decrease it.
Okay. Okay, so Roman, the aim of this past paper practice is to show you exactly what to write, and I think I did that. I showed it to you last class when we spoke about transformers, exactly what to write, because if you have thoughts all over the place, you wouldn't be able to just hit the exact answer and the exact terminologies that the examiner needs you to write down. How a transformer works is a question, and please keep up with me if you have a pen and a paper. How a transformer works is divided into 3 sections. 1, an AC current or an alternating current in the primary coil creates a changing magnetic field. That's 1 mark. This magnetic field is transmitted to the secondary coil by the soft iron core. Okay? The secondary coil cuts the magnetic field lines, inducing an EMF. Okay, is the answer for this question, and this is exactly what you need to write when it comes to how does a transformer work. Okay, it's all about voltage when you come and explain transformers. EMF is voltage. EMF is electromotive force. So a transformer changes a primary voltage into a secondary voltage. But how does it do that? That's the question when they say how a transformer work. This is the details behind how a transformer work. Does that make sense?
Yes.
Good. Moving on. Please write that down if you haven't written it yet. Now, state one way in which energy is lost from a transformer and from which part it is lost. We've discussed that. Say one way in which energy is lost. How is energy lost? And from which part? Any answers? Any suggestions? Because when you look at a transformer, you have a primary coil, you have an iron core, you have a secondary coil. From which part is the energy lost?
Core.
The core. Ask
The
her.
iron core.
The iron cores, and state which energy is lost. When they say, okay, right now you just said which part, but how is it lost in the iron core?
It transfers from the primary coil.
It does what?
Transfer from the primary coil.
This is how energy is lost in the iron core. Now there is no definite answer for this question. You can say, okay, energy is lost in the iron core. Energy is lost as eddy currents. Okay, that's an answer. Or you can say energy is lost in the primary and secondary coils. How is it lost in the primary and secondary coils? They're lost as heat due to resistance. All of these are correct answers, but most of the energy is lost in the iron core due to eddy currents. Okay, that's why the iron core is laminated, and I stated that in the last lesson. We talked about the iron core and the lamination and what's the meaning of laminating the iron core. Okay?
Mr. Asad?
Yes.
I'm sorry, but can you tell me what an eddy current is?
An eddy current is when you have a transformer. This is your iron core here, 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 and you have your primary coil. Then it produces a magnetic field. Okay, this magnetic field, which is produced by the primary coil, is transmitted through the iron core. And then it's cut by the secondary coil, inducing an EMF. Now, some of the magnetic field lines are cut by the iron core, and there is a current, created in the iron core itself. This current created in the iron core, it's like circles or whatever, so in the syllabus, but the current created in the iron core is called eddy currents. Okay, now what you need to understand when it comes to transformers, the transformer core does not carry any currents. It doesn't carry current at all. But sometimes if the iron core is not laminated good enough, it carries current called eddy currents, and these eddy currents causes energy to be lost in the transformer. Good, these are eddy currents. Okay?
Okay, thank you very much.
Now, when we look at this, shows a device labeled IGCSE transformer. It transforms 230 volts AC into 12 volts DC. It transforms AC to DC. That's something that we need to know. What is the output of the device? Okay, let's answer that real quick. What is the output of this device?
A secondary coil.
Come again?
Is it 12 volt? Like, do you mean the voltage or like
yes,
the final part of
yes,
the device?
The voltage. Yes, the voltage.
It's 12
volts DC.
volts.
Okay. From the information on the case, deduce what other electrical component must be included within the case for the IGCSE transformer apart from a transformer. What else is inside this device other than a transformer? We haven't stressed on it yet. We haven't talked a lot about it, but the other device that changes, I think we just mentioned it sometimes, it changes AC to DC. It's called a diode. It changes AC to DC. Okay, this is something that you need to know, and we'll talk about it today as well. So a diode changes AC current to DC current. Good? Okay, now we have this question. It says that a transformer supplying electrical energy to a factory changes 11,000 volts to 440 volts for the use of the factory. The current in the secondary coil is 200 amperes. Calculate the current in the primary coil, assuming no losses from the transformer. So when they say no losses, it means that the transformer is 100% efficient. So the power input is the same as the power output. So power input equals to power output. I want you to use this formula to answer this question. V1 I1 equals to V2 I2. V1 I1 equals to V2 I2, where V1 is the voltage in the primary coil, I1 is the current in the primary coil, V2 voltage in the secondary, I2 current in the secondary. That's the formula you need to use. And this is the information you have. Substitute and find the answer real quick. And write the answer on the chat. Omer says 8 amperes. Nujud, the question simply tells you calculate the current in the primary coil, which is I1. They want you to find I1, Nujud. They gave you V1, V2, and I2, and they want you to find I1. Eight amps. 8 amps. Okay. 3, I don't see your answer. Sama, I don't see your answer as well. Can you show the formula again, sir? The formula is, I'm gonna hide my solution. The formula is V1 I1 equals to V2 I2. Okay, so yes, this is the final answer, which is 8 amps. Right, the final answer is 8 amps. V1 I1 equals to V2 I2. Good. All right. So. Question 2. This is only one question. Question 2. So let's have 10 minutes break. Then we will continue with question number 2.